Yep. Like Dr. Matthews said, we have a long history of collaboration, so you might see a few throwback images of Dr. Matthew. We'll see what happens. So thank you for inviting me. Today I'm going to share my path from postdoc to mid-career faculty, and I've been at the same institution for that entire time. So my experience might be a little bit different, or maybe some of you are going through that right now. So I'm going to talk about my lab a little bit, how I got here. I'll talk a little bit about research and then kind of frame it in terms of some lessons that I learned. Feel free to interrupt me at any time for questions, and hopefully we'll be done a little bit early and you can ask questions then too. All right, so I do computational biomechanics. I'm a section of biomechanics director, but my lab is called the Computational Biomechanics Laboratory. And just to give you a little bit of background about what that is, first of all, biomechanics is the study of structure and function of biological systems by means of the methods of mechanics. So my lab does biomechanics, but we're a computational lab. So it's relating to the process of mathematical calculation. So if you put those two together, my lab investigates orthopedic implants, natural joints in vivo, behavior, failure, disease processes, all with computer models. And I'm going to talk a little bit about the orthopedic implants angle in a little bit. First of all, these are the faculty members and graduate student who are currently working in the lab. Jonathan Gustafson and Stephen Mell are instructors at Rush. They were formerly postdocs, but now they are forging their own independent path. Michael Godoy is a PhD student. He actually did his undergraduate at UIC in biomedical engineering. Then we always have various undergraduates and medical students who come through the lab. Lubna Shah is one who's been with us for quite a while now. All right, so back to what the lab does. We focus on problems that limit the lifetime of joint replacements, and we try to mechanistically investigate current clinical problems. So many of you may do bench research, so this may sound a little bit different, and it is a little bit different. It's a little bit, we do very applied research, but we still have the same goals in terms of a disease or certain intervention that we're testing. So we try to mechanistically investigate current clinical problems. We perform large parametric studies with our computer modeling. And the goal for this is really to help reduce the number of physical prototypes that you might need if you're doing a physical test with implants, and efficiently optimize design parameters. So a little bit of rationale for the work I do. I said that I investigate joint replacements, so it's important to know, why do joint replacements fail? And this is some joint registry data that shows for hips and for knees, there are various reasons of failure, even though the vast majority of total hip replacements perform very well. When you look at why they fail, these are the specific reasons. And currently, the Computational Biomechanics Lab investigates metallosis, which is how your body reacts to metal debris in your joint. And this can be shed from modular junctions of the parts of the implants that fit together. It can be from wear in the case of metal on metal implants. This graph is a little misleading. The very high percentage that fail due to metallosis, most of these were due to a different type of bearing surface, which is metal on metal, rather than polyethylene on metal we have today. I'll get into that later. I'm just trying to give you a really brief overview of what we're investigating. And then with total knee replacements, we investigate the problem of loosening. Loosening can occur because of mechanical loading. Late loosening can also occur because of the body's biological reaction to polyethylene debris. So we're developing computer models to investigate these two problems. And because we do computer modeling, We also collaborate with a lot of different people inside Rush and people outside Rush as well. So I mentioned throwback Dr. Matthew by the knee simulator at the tribology lab. We collaborate with the tribology lab. They do a lot of physical testing that we use to validate our models. We collaborate with the motions lab so that motions that you measure from humans can be applied to the model. Depending on what the clinical problem is, we might collaborate with all different labs at Rush. And certainly we've had a great collaboration over the years with Rockford, with Dr. Matthew and Dr. Biju Kumar. Okay, so my career timeline. So I did my undergraduate and PhD at the University of Iowa. So I have this kind of history of staying at the places where I start. And then I went to Rush as a postdoc, and now I'm faculty. So I just put down some of the funding sources that made this possible. And since this is kind of a mentoring talk, I put this down to show how it's, you know, you might not have huge sources of funding all the time, but you might have smaller sources of funding that kind of contribute to being able to make progress on a project until you can kind of get by, until you get larger grants. So part of my postdoc at Rush, I had a small individual grant, but my mentor had a large R01 and I had a large role in that R01, which really helped me gain experience in project management, helped me be somewhat independent within a larger umbrella. But I also had the individual one where I really could just take the research wherever it went. And it was really up to me to define that direction. So then once I was faculty, I had some smaller pilot grants, which led up to the different NIH grants, one of which I'm co-PI with Dr. Matthew. So mentoring played a huge role during this time, and today still mentoring plays a huge role. I was provided with training that was critical to my development, not just scientific, but I guess so-called soft skills in terms of networking and how to communicate your research. So during this time, especially early on, it developed my professional network, which with the help of mentors, and these are now collaborators, and I could see some of them being collaborators in the future. I was lucky enough to be able to participate in an organized mentoring program, which provided access to a huge mentoring team, even if they weren't, you know, mentors that were specifically assigned to me. They were kind of committed to mentoring the group as a whole. And then I also put a huge focus on peer mentoring. So I have several of my peers who I consider mentors, and I think that they consider me mentors, and we're constantly talking through things and bouncing ideas off of each other. So I have a few early career lessons learned, and the reason I'm putting these here at the beginning is because I'm going to come back to them later during the talk when I talk about the science part, and how, you know, these things really came up along while I was working on my science. So the first thing I learned is that juggling multiple projects, which I'm sure you all do, is very tricky. And so for me, I focused most of my time on my main project early, or the main project would be, you know, if I wasn't independent yet, it would be the one that my PI had funded me to work on. Or now when I'm started to be more independent, it was the one I was most interested in, or it had some pilot funding. And then the rest of the projects that I was interested, I just try to carry them along, make a little bit of progress, until finally maybe I get some more funding to you know, get students or postdocs to help bring those projects to really you know, as far along as the other one. So I really try to early on tried to focus on a main direction, and then other things I was interested in, just make continuous project progress, but it's okay that, if they couldn't develop as quickly as the main project. Small pilot grants are great. They offer a lot of flexibility even later in your career. Don't always have to just go for the big grant. They're often more flexible, and they can really help you start up things that you wouldn't be able to start otherwise. As an early career, of course, you may not be independent fully yet, but you should still feel free to assert your independence. You're an expert in your area. Even early in your career, likely your PI recruited you because of the special skills that you have. And if I have a new postdoc, I want them to be as independent as they can be. Because yeah, they're the ones who have the expertise in their specific work that they did. And then this is a huge one: develop a strong core of peer mentors. So if you might have a mentor assigned to you through a program, or you have your PI as a scientific mentor or as a later career mentor, but at the same time seek out peers, because there's other issues, especially if you're staying at your own institution. It always comes along with interesting mentoring situations. If, say, you transition from a postdoc to an early career faculty member, and perhaps your same PI is there, it's always tricky to have to navigate. But if you have a strong core of peer mentors, you can help each other and talk about it with each other. And then the last one is be flexible, be open to new collaborations. This brings new creativity. I know that if I hadn't been open to collaborating with Matthew, or if Dr. Matthew is actually the expert collaborator, I would say. So if I hadn't started working with him, I very likely would not have this NIH grant that we've been working on, and wouldn't be so far along in the science of the hip part of things. So it's important to foster these collaborations. Try to think of small projects you can do that lead to something real, like a real publication, even if you can't get funding because it's just too early on in the process. All right, so that was a lot of stuff I threw at you, but I'm going to come back to each point as I talk a little bit about some science. So how did I get to Chicago? So I started out my PhD at the University of Iowa, had to do with total hip prostheses. So you can see the left is a example hip prosthesis, the top part with the ball that goes on top of the femoral component and the acetabular cup. And on the right side is this computer model. And this is one of the first things I worked on with my PhD. So we're interested in looking at how if the metal surface becomes roughened, you can kind of see that it's much duller here than here because this one is scratched. If this happens, how does wear of the implant change? This was at a time when polyethylene wear of hip implants was kind of a major reason for failure that limited the lifetime. Now there's newer materials, so they are expected to last much longer. But at the time, if your hip implants lasted 10 years, that was great. But now we're to the point where we want them to last your whole lifetime. So this is just some example of a computer model that I worked on during my PhD. So then I came to Rush. I was lucky enough to have several different senior mentors. Dr. Marcus Wimmer at Rush in orthopedic surgery was my main mentor throughout my postdoc time and early faculty time. Also, Dr. Natarajan, a professor at, if you were in bioengineering at UIC, you might be familiar with him. He does computational biomechanics as well. Sadly, he passed away last year, but he was definitely a subject-specific mentor for me because we're the only two who did kind of the computer modeling finite element analysis at Rush. And then Dr. Sumner is the chair of cell biology and molecular medicine at Rush, and he ended up being one of my mentors as well, because while I was a postdoc, he was the PI of a T32 for postdocs, and I started out my postdoc being on that grant for a little while. So my research was related to knee implant evaluation. Like I said before, I was lucky enough to have a very small NIH grant as the PI in F32. And then I really worked as a co-I for quite a while on an R01 from my postdoc mentor. So I said I worked on knee implant evaluation. So focus on kind of the top line, the top half of this slide are things that I worked on as a postdoc. So I had done this kind of on the bottom, finite element analysis as a PhD graduate student, but starting my postdoc, I switched a little bit and I switched into musculoskeletal modeling. So with musculoskeletal modeling, you create this computer model of bones, joints, and muscles. You can, as inputs to the model, you can apply motions that you measure in a motion analysis lab. But the goal was to predict the internal forces that occurred across the knee joint. So we were predicting how high the load was. And that might sound like, well, why can't you just put a sensor in there? And you know, if they're having surgery for some other reason, they do have some instrumented implants, so then you could put a sensor in there. But really, there's no way to predict knee forces without, you know, something very invasive without having a computer model. And because there's so many different muscles that contribute, you have to use some kind of optimization techniques to figure out how they contribute to contact force. Okay, so I mentioned that one of the things that I recommend as an early career is focus on your main project, but bring the other stuff along that you want to do. So I had gotten away from finite element analysis, which I'll describe in the next slide. It's related to the bottom here, but that's what I did as a PhD student. So I kind of slowly worked on this a little bit as a postdoc, and then as I started my early faculty career, I kept the musculoskeletal modeling, but really focused back on finite element analysis, which is what my original training was in. All right, so what is finite element analysis? And if you guys want to use the participant, let's see, I'm not sure if this will work. You guys can give me a thumbs up if you know what it is or if you've heard of it before. Let's see, do I see any thumbs up? And it's okay to not have. Oh, I see one. Divya, yeah, you guys are cheating because you've seen talks like this before. Matthew too, cheaters. Okay, so finite element analysis can determine the internal stresses of complex structures. It's used in virtually every field. So I can guarantee you haven't walked in a large building that has not had some sort of finite element analysis related to it before the building was built. You haven't driven in a car that simulations weren't performed by finite element to make sure that the car was safe. Same with airplanes. So it's been, you know, present in automotive and aerospace industries for a long time, but it's much newer in orthopedics. So it wasn't until, let's see, wasn't until the 70s that it was introduced into orthopedics. So here's an example of the first finite element model in orthopedics. It's of a femur. It's a two-dimensional model, which is split into a bunch of boxes and triangles, which are the elements of the finite element model. So since the 70s, you know, there's been just this huge increase in the number of citations, number of published articles, and now it's pretty mainstream in the biomechanics literature. If you just open up any biomechanics journal, you'll see some sort of one of the articles will have something about finite element analysis. So what you do is you break a large complex problem down into smaller, simpler problems that can be solved using mechanics equations. So we're representing, in this example, we're representing this continuous part, this pelvis, as a discrete object with nodes and elements. So you might break it down by region, and then within each region, you'd perform what's called meshing, which breaks it into these cubes, and then at the corners, the points at the corners are called nodes. So you can do physics equations on each cube to determine stresses and deformations throughout the entire pelvis, and then in the computer model, it links all of these together. So some important things to note are that you have to decide what your area of interest is. So in this one, it's not just the pelvis, it's also with a hip joint. So they've modeled the femoral ball on the hip joint and the liner, and then this kind of metal revision system. But they kept out the femur because that's not their area of interest. So it's up to the analyst to determine how much of the model is important. Okay, so the first kind of FEA, sorry, if I say FEA, that's finite elements analysis. The first thing that we did was we created a model of total knee replacement. And this work is from Dr. Stephen Mell, who was a graduate student with me and is now senior at the end of his postdoc. He's an instructor now, working towards independent faculty at Rush. So this is a total knee replacement finite element model. It's of the distal femur and proximal tibia component. So this component would go on the ends of the bones of your femur, and then the green part is made of plastic, and it goes on the end of your tibia. There's also another metal part that would in real life be right below the plastic component, which is the part that interfaces with the bone. So one of the first things we did is we were interested in knowing if the motions and loads that are applied to total knee replacements are for preclinical testing when they create new designs are representative of how actual patients move and walk. So this is the first example of where I combined my postdoc work with my previous experience in finite elements. So I had to use the postdoc model where I calculate forces and apply it to this new finite element model. So this lower left box shows the average motions and loads for patients who have total knee joint replacements. So there's quite a bit of motion. It might be a little hard to watch because your tibia would be fixed and your femur is moving. And usually if you think about someone walking, you'd think about it kind of the opposite, that your tibia is moving. But then you can compare that to the lower right, which is patient motions for walking upstairs. So walking upstairs has more flexion, looks like maybe some more sliding, but it's not that dissimilar at the knee joint, besides more flexion, it looks like. So then the top line are what mechanical knee simulators apply when they're testing total joint replacements, endurance testing them to see how they will, how to try and predict how they'll react in the body. So the point here is that these motions are much smaller than what we had measured for actual patients. So that could have implications for how this test behaves compared to when the joint is put in someone's body, how it behaves. So the kind of heat map that develops, those are stresses in the plastic part of the component. We also calculate volumetric wear of this plastic using a computer model. So that I was just kind of showing you comparisons of stress and comparisons of motions, but we actually wanted to predict how much wear would occur for patients using this model. So we coupled it to a wear model that was developed on this test system using a wheel on flat configuration. and we implemented it into the model so that as one of those walking cycle motions are applied, the nodes and element locations on the surface of the plastic are updated based on the predicted wear. So as more and more cycles are applied, how would you predict the surface geometry to change due to volumetric wear? And we validated this compared to simulator testing and found a good relationship for the different test metrics that we used. So we consider this to be a well-validated model when you're comparing the predictions of the model to predictions of the simulator. Okay, so this actually is a pretty detailed computational workflow. We have our finite element wear model, and then we can do lots of pre-processing things to the model to change how the model behaves, and then we can determine the effect on output variables from changes to those input variables. And this is all linked up in a design of experiments execution where we get some statistical models out of it at the end. And Stephen developed this during his PhD and has been expanding it from his postdoc. So I'm going to give you one example for how this framework works. So remember I showed those animations of the total knee replacements, and I said that the machines apply motions in standards for preclinical testing. So this is an example of those motions. We have flexion, axial load, and then some other secondary motions. But when you compare that to the patient data that we measured in the motion analysis lab, you can see that flexion and axial load look pretty similar, but the other secondary motions do not look the same. So we wanted to know how this affects wear of the joint because of these differences. So we hypothesized that changes in force input would be the primary driver of wear. All right, so Stephen developed this pretty cool method that varies our input loads and motions over this kind of range, and then developed some code that can create a waveform for any arbitrary curve within the shaded regions. So this is how we could vary individual motions and loads, apply them to the finite element model, and determine what their output on wear was. And he ran 310 simulations. Okay, so volumetric wear ranged from the low 10s, ranged from just under 4 to 6 millimeters cubed of polyethylene. That's what the plastic is. Depending on the input. So the extension peaks had the highest effect on wear, and contrary to our hypothesis, the changes in axial load weren't the primary driver. It was primarily flexion extension. So that was interesting to us. We didn't necessarily expect that. Excuse me. And then we got a statistical model out of that. So if you wanted to determine what the effect on wear was from those variables without running finite element analysis, you could plug the numbers into a statistical model and kind of have this surrogate model that would help you predict wear. So this is a regression model. And yeah, you could say if you had an individual patient, you could say what their motions and loads are and find where they are on this specific curve. So that was kind of Stephen was there for my very early career up until now, and this represents pretty large body of work. That was probably half of the lab output during that time. So earlier at the end of my postdoc, I started working on a different project, and it was a new direction for me, a new NIH hope. And that was to switch to the metallosis issue that I talked about early and modularity of total hip replacements. So modularity can lead to taper fretting corrosion and adverse total tissue reactions. So here, this is a head-neck modular junction. So during surgery, the surgeon puts the hip implant into the femur, and then they hammer on a femoral head onto this component. The opposite here, these components go in the pelvis. But after a period of years, some of the taper surfaces look like this. You can see there's what looks like damage on there. And if you look closely, this particular one has some significant damage to the metal surface. So what happens in the body is your body reacts to this metal debris. You can get necrotic tissue. This is all necrotic tissue, and what we call adverse local tissue reactions. This black stuff is the fretting corrosion products, the metal debris that are coming out of the joint of the modular head neck modular junction. So the ball is down here and the hip stem is up here. So there are a lot of different factors that can lead to damage and total hip replacement modular junctions. And our goal was to just systematically try and determine the effect of different factors on damage of modular junctions. So with this project here, it got started because of an RO3, a small grant. And then after I got the RO3, I was able to recruit a postdoc to the lab, Jonathan Gustafson, who's now an instructor in the department. And that really helped push this forward, you know, even farther than I could do on my own. I also now have a PhD student working on this because Michael Godoy, because we have a larger project of an RO1 with co-PIs Robin Porzel and Dr. Matthew. This is an old image, but it's still close enough to what we're working on today. So basically, I was able to start this project by, you know, Robin and Matthew had been working in this area and kind of Robin suggested that this topography might play a huge role. And that's a perfect problem for finite element analysis, is to look at how the structure of a surface changes the contact mechanics. So did a little bit of pilot data, was able to get the RO3, which allowed me to have funding for more personnel to have a larger project in this area. So I could kind of bring stuff along until I could pay for more people to help work on it. I had to be open to the collaborations, and this is a, you know, pretty creative endeavor that definitely would not have happened if I hadn't had some excellent peers to collaborate with. All right, so I'm going to give you a short overview of some of the work that we've done in the area of taper corrosion. So I also mentioned that we collaborate with a lot of different labs. So in order to have a good finite element model, you have to have input from physical specimens to make sure that you're modeling the right thing. So in the implant pathology and retrieval lab, we measure the dimensions on total hip replacements, approximate it in our model, then create a model that's really relevant to what actual hip replacements look like. So you can see the surfaces here are grooved. These are machining lines, and we are implementing those machining lines in our model of head neck modular junctions. So we approximate it as this wave, and then we can put it in the model. So this is an example finite element model. This is a 2D axisymmetric model, unlike that 3D model that I showed you earlier for total knee replacements. And so it's axisymmetric. So we have a line of symmetry running through the model, and it's just a half cross section of the stem taper and the femoral head. And then at the surfaces, we have this, these machining lines modeled on both sides of the components. So then we can apply an assembly load and look at how these machining lines or microgrooves change in terms of permanent deformation as the femoral head is assembled onto the stem taper. So here's an example result. So this is an exaggerated topography. It is one that we have measured in the lab, but the majority of them are a little shallower than this. So you can see that there's high stress concentrations that occur in the peaks of the machining lines, and then you get this flattening that occurs, and there's a lot of permanent deformation. So the final contact mechanics are very different than if you had just assumed that these surfaces were flat. So I talked about validation with the total knee replacement model, and the same thing with this model. It requires validation to make sure our predictions are within what actually occurs. So Dr. Gustafson measured the deformation, the flattening of machining lines on a bunch of retrievals in the lab and compared it to his computational results. So just visually, this is kind of a qualitative comparison here. He did quantify these numbers, but I'm just showing it to you qualitatively for now. You can see that the flattening looks like what's measured in the lab, and then this kind of like pile up on the end is pretty similar too. We also did a more formal validation where we measured 4 different stem tapers, applied an assembly load in the lab under very controlled conditions. This was a collaboration with Zimmer Biomet. Then we cut the femoral heads off, measured the surface topography again, and then compared it to our results from our computer model. And the results fit pretty well. The orange is FEA and the blue is the experiment. So all along the stem taper, this is the change in dimensions, and it falls within the lines pretty well. So the other thing that makes this experiment pretty difficult is the flattening that we have. The maximum in this example was only like 5 micrometers. So that's a difficult physical test to perform when you're trying to measure different changes that are only 5 micrometers. Even though computationally we can change things and measure it. We don't have trouble with those types of calculations simply because it's all a computer simulation. All right, so back to this. I showed you this example for this kind of more extreme microgroove geometry or machining line geometry. This is what most of the microgrooves look like on real hip replacements. This kind of amplitude of microgrooves on the stem taper is about 11 microns. This distance from peak to peak is about 200 microns. And then on the femoral head side, this is only about 2 microns high and about, I think this one's 25, the distance between the peaks. So what happens during assembly of the implant is you get flattening. This is a metal femoral head, so you get flattening of the surfaces on both sides, and you might end up where one peak of the machining line on the stem taper side has multiple peaks on the head taper side. So we have a pretty big difference in contact mechanics simply due to the geometry of the machining lines alone. And the colors in this picture are stress. So red means high stress, and the very dark blue is no stress at all. So the other thing you see here is that this isn't in contact, but there's some stress, residual stresses in the surface because of this permanent deformation that occurs. So these are regions that could be open to the material, could be susceptible to different corrosion processes because of the residual stresses. So in this finite element simulation, we're determining mechanical differences due to the surface geometry, but certainly this could have implications on the chemical behavior of the surfaces, which we go to Dr. Matthew to simulate. All right, so just showing if you have a smoother, if you don't model this geometry on the head taper side, you really get very different contact mechanics, and it might not be relevant to what's going on in the body. So if you're going to make predictions about how total hip modular junctions behave in the body, it's important to model the real surfaces as much as possible. And then just a few results of what happened when we changed the dimensions of our machining lines. You know, um, the steepest and most narrow spaced machining lines led to more localized contact, lower contact area, but higher stress and plastic deformation. So I can't definitively tell you what situation is best in a total hip implant, but certainly something where you have more flattening of grooves with high stress would mean you have kind of a stable femoral head after assembly, where hopefully it wouldn't move around as much after it's assembled. So I keep talking about this assembly process. And so one thing we wanted to investigate next with the model is, how does this assembly method affect the change? What happens if the surgeon hits it really hard, or what happens if they use multiple hits to assemble the model rather than just one hip? So we have this this sort of simulator, this benchtop setup, where we have a femoral head and a taper, and then there's a load cell in here, so we can measure the three-dimensional force vector that goes through because of the mallet hit. There's also a load sensor up here before the femoral head to determine the actual magnitude that the surgeon applied before it goes through all of this material. So when we tested a bunch of attendings, fellows, and residents, surgeons who had all been trained in doing this, and the attendings, you know, do multiple hip surgeries each day, we found that the total forces were about 8 kilonewtons. Now, our model had really been investigating the effect of 4 kilonewtons. So what that told us, first of all, is that we probably want to simulate higher forces, because that's what surgeons are actually doing in the OR when they assemble it. The second thing that was interesting was that there's a lot of variability, and most variability was in these trainees, the fellows and residents, and the attendings really were pretty consistent. So there may be some sort of training effect. Maybe in the future we could use a simulator like this to provide feedback for fellows and residents, but we're, you know, that's way down the road. For now, we just wanted to know what kinds of loads are surgeons applying, and we also measured it three-dimensionally, so in the future we can determine the effect of using a fully three-dimensional load. So I mentioned that some of the surgeons hit it multiple times instead of one time. So with the model, we decided to investigate that. So here's our input load for a single hit. This is actually measured with that device, and we apply this to the femoral head and see what the resulting contact mechanics are. The other scenario was you have a small strike followed by larger and larger till the third strike, and you end up with the same overall magnitude. And this is what we were seeing occur in the laboratory, where some surgeons did this, some surgeons did the one strike. And what we found is that you get much less plastic deformation if you do this three-strike sequence, likely due to changes in the material after that very first hit. You get some hardening of the strain hardening of the material. And so then you get less flattening overall. And we think flattening is important because then it increases contact area, might have a more stable construct. So this needs a lot more research, but we think that, you know, we can determine the effective assembly method and actually see how that relates to the behavior of the implant. So I talked about just a few things that go into damage of total hip replacements: surgical assembly, and then surface topography, but we definitely are investigating the other variables that go into this. And then in the lab, there's a ton of work done by Dr. Matthew, Dr. Vijay Kumar, and Dr. Robin Porzel to look at some material effects, to look at the corrosion properties, and then biological effects, because these happen in the body, not in the lab or in my computer simulation. So certainly the presence of cells and you know, different electrolytes that are present in the body make a difference. All right, so coming back to one of my first slides, I kind of gave you examples from two different things. So my goal as the director of a lab is that I create models that can be relevant to a lot of different situations, both failure situations, but also good situations. You know, we want to know what happens when implants work correctly, because that gives us ideas about designs for the future. So we've expanded into some of these areas a little bit. And my goal as I move forward in my career is that I can kind of continue to expand models to predict a wide range of failure mechanisms. So this is the same, my career timeline that I showed before. And I put this PhD comics up here because I think this is really what actually happens. You're never just writing the grant, getting money and doing research and publishing. It's this cyclical process where you do a little bit, you try to get some funding for it. You know, you have to do a lot of things along the way. You have to resubmit proposals multiple times. So it's important to be persistent and just stick with it because it's not an easy process. So since this is a mentoring talk, it's perfect that Dr. Matthew asked me to do this on January 27th because it happens to be National Thank Your Mentor Day. And January is National Mentoring Month. So I'd like to thank my mentors and my peer mentors and encourage you all to thank your mentors today and think about mentoring during the month of January. So here's the lab members in a picture at a conference. I have lots of other collaborators, too many to mention here, and then some of the funding sources. So I'm happy to take a few questions about science or not science. And I don't think I put my email up, but I'll add it to the slide. I know the slides are going to be posted somewhere, so I'll add it to the slide so you guys can contact me offline if you want to. The last thing I want to say is that Rush has a T32 for postdocs right now. So if you are if you know someone who might be looking for a postdoc, please encourage them to, you know, contact me or you can Google T32 Rush and you'll find the information and apply. All right, thank you.
Thank you, Hannah. So this, I think she was talking about her research and how she moved from postdoc to where she is now and developing her own lab and having the associate professor status. So it is a time for, like, I know most of the attendees have some questions and maybe they are in a transition, maybe they are just beginning their postdoc, and maybe they just started their faculty position. So all these different stages, and you know, yeah, of course you can chat, put in your chat box, or if you can switch on your mic and ask questions. Yeah.
Sure. So first I can answer the question in the chat box. It says, will you please comment on the importance and strategies to communicate with funding agencies, for example, NIH program officers? And yes, this is very, very important. It's something that's not necessarily like, you wouldn't think that it matters, but it is important that they kind of, the program officers at NIH recognize your name and can kind of link it to a conversation with you, because at the very end, they do have some say with the final ones that get funded or not, if you're close to the pay line. And they can give you really valuable advice about how to move forward. You know, if you're doing the right mechanism, if your aims are appropriate for whatever institute that you are targeting. So for example, I've contacted my program officer before submitting a grant, and then I always do after a grant when I get the review. And, you know, program officers are very busy. There's, you know, hundreds of grant applications. So you have to be a little persistent with that, but it definitely is worth it to talk to them. And some of them will even kind of look at your aims and decide, and will tell you like, yes, I think we'd be really interested in seeing this, or maybe if you had this focus, it would be more relevant for our institute, something like that. That answer the question? Are there any more questions related to that?
Thank you. That's very helpful. So like if you send the aims to the PO, you mean the specific aim page, sometimes you can also send to them, right?
Sometimes, yeah. It varies based on the program officer. Like I've never done that with my program officer, but I hear my peers talking about that all the time where their program officer said, well, yeah, send me your aims page. I'd like to see what you're thinking.
Yeah, sure. Thanks.
Any other questions? And I have maybe a general question where I know like your transition and a lot of, of course, it also gives some lot of stress and all these things. How do you manage with your family and all this? Do you have any thoughts?
Yeah, so it's hard. Regardless of what your situation is, it's hard to balance different things, right? So I also had I took 2 maternity leaves at the beginning of my faculty career, and for me, everything was great. I didn't really experience any setbacks from that. I was very lucky, and I felt like the timing for me worked out really well, simply because each time I had put grant applications in right before I left for my maternity leave. So I felt like even though I was kind of stopping work for a little while, things were still in the fire, I guess. Irons were in the fire. Yeah, so I had submitted proposals right before each leave, if that works for you. Now that my children are young and starting school, I have a pretty flexible day, so I just try to lead my team that it's okay to be flexible. Of course, it depends on it depends on what type of work you do. If you have certain bench experiments, they have to be checked at certain times. But for me doing computer models, there's no reason that I have to be in a lab versus at home, as long as I can get to my computer. So my team and I are really flexible in terms of, I have to work from home, and I have a child home with me today, so maybe I'll be working on a weekend day instead of a weekday. Be kind to each other and help each other through that. Now, if you're in a more traditional situation, that might be a little bit harder. But that's how I've managed it, with just trying to create this environment that it's okay to be flexible and have different work arrangements, as long as everybody has the lines of communication open about it. Did that answer your question?
Yes.
Oh, I see there's something in the chat.
Yeah.
What are the,
Yes,
Divya asked, what are the criteria to prove independence in the career? Okay, so the main one is that you're getting grants as a PI. If you're starting to get your own funding, you are considered independent. So in my position, it's pretty hard to completely cover your own salary 100%, just because we don't have as many teaching responsibilities. I'm like 90% research and 10% teaching. So covering that 90% isn't necessarily the I guess the benchmark for independence. It's more like, if you're submitting grants as a PI, your papers have moved from only like first author to like more last author, like people will consider you independent. The other thing is, each institution has their own, promotion criteria, but for ours, a decent part of it is, do you have a regional reputation when you're moving from assistant to associate? So if I were looking to, if I'm already an associate professor, but if I were up for promotion as associate professor, even giving a talk like this regionally in around the Chicago area helps my regional reputation. So, oh, people are asking her to speak at different places, then you're considered more independent for that reason too. And of course, many of you as postdocs already may have like scientifically, a national reputation already. So certainly that goes towards being considered independent. But yeah, in reality, the main measure is probably that grant success, I'd say.
So if no, I have another question. Dr. Lundberg, I think your experience, it's very interesting, and I think it's very useful. Like you showed how you build this model and how you go different steps along the career path. So I have a question. It's because now, especially NIH, the grant is very very competitive, especially for the younger researchers when they start. So I just wonder whether you have any comments or suggestions when you face a lot of, if the younger researchers when they face a lot of failure when apply the grants, and at this kind of relatively downtime, what is your suggestions, and then how you can maybe inspire yourself or inspire other people, and how they can maybe fund at this time, how they may support and to go to the next stage.
Yeah. So yeah, I mean, grants are incredibly hard to get right now. It's actually, I think, as hard as it's ever been in my career so far. So my suggestion for the early stage faculty or postdoc is, you have to be really persistent. You have to let it just roll off you and keep submitting. If you submit an NIH grant 3 different times, that's not weird at all. There's people who submit it 6 times before it gets funded. You have to be persistent. I mean, you have to take criticism and keep improving and everything. You can't just submit the same thing and expect something to change. But certainly just let it go and keep working on it. As long as you can improve it each time, you will get it eventually. But also, you don't have to stick with just NIH. Work towards, if you're at UIC, you probably have a pretty good chance with other funding with NSF. Look at foundations. Anything helps. Even something small helps. It makes your bio sketch look better for bigger grants. So they are definitely worthwhile. And then the thing I'd also say is, if you're early career faculty, is to pay attention to your early career, the 10 years from the end of your PhD, where you can be considered an early career researcher through NIH. In my institute, they actually give different pay lines that they set for early career versus established investigators. And that can make a huge difference. So the R01 that I keep mentioning with Dr. Matthew and Dr. Porzel, we actually got that grant because we were all 3 early stage investigators. Our grant didn't score high enough to meet the pay line if we hadn't been at that stage. So that made a huge difference. So just stick with it earlier on in your career and try to make the most of that time.
Sure. Thank you. Yeah, that's very great suggestions. I think there is another question in the chat.
Oh, okay. Tips on how to actively collaborate with other researchers, and then soft skills, hard skills, and other factors. Okay, so first, in terms of actively collaborate, so early on, I went to a lot of different seminars within the department. Like every time the department had one, I went. Now, I mean, I still go to most of them, but it's not quite the same active engagement. And mentoring program things, so different presentations from people outside my department, I do the same thing. And that was to really see, is there anything that, we can find common ground on, even if it's very small. NIH likes to see that. They like to see that you're collaborating across different areas. So I just say, go to as many things as you can, ask questions, approach people afterwards. I think most people are interested in collaborating, as well. So they actually appreciate it when people approach them. And Matthew can probably give you a lot more advice on that front, but that's what I did. And then in terms of soft skills and hard skills, so I am not someone who necessarily enjoys kind of speaking, I don't enjoy promoting myself, but early on in my career, I looked at it as I'm going to get better at speaking, and, having a presence, because I need to do this. It's just part of my job. And so I'm going to practice. So I made my lab meetings more, presentation is kind of expected all the time, and really, fight against what I want to do, which is to just like work on my computer and create models, because that's what I think is fun. So the soft skills type thing, it just requires practice. So if you have access to mentoring program seminars or workshops, take them, and like if they want you to practice elevator speeches or different things like that, take it seriously. I think it does help when you actively work on those communication skills. As far as other skills like grant writing, I took various workshops early on in my career that I did find really helpful. And then, just peer review. If you find a group of peers who are willing to help each other, I never worry about the kind of competition type things. The research I do is so weird that like who's gonna like take an idea or something like that. So I'm really open to have a lot of people review and look at my grants, and I'll do the same for them, because if somebody else in my department gets a grant, that's great for me too. It helps with infrastructure, etc. So like the goal is that we're all successful, I guess. And I try to find collaborators who have the same attitude.
Yeah, I think what Anna said, I totally agree. And in my thought is, I think as the constant updates each other, and and also have some. Most of our collaboration started with the coffee time.
Yeah.
Have some coffee and discussion. If communication is not there, you lose the trust. And that if the trust is gone, collaboration is gone. I think that will reflect in so many ways. And I think that's why I think the coffee time is very important, to have some talk and discussion. And I always remember at Rush, we always have lunch together. So a lot of great thoughts comes when you have this lunchtime. And but it's a small thing, but that's a greater impact, how these continuous collaborations.
Yeah, and then after you have your coffee break, follow through with plans you've made. If your collaborator is excited, enthusiastic, and actually does something tangible, that just encourages everybody to actually start something.
Yeah, I know that time up now, and of course, I know you may all have so many questions, and you can always reach out to Dr. Lundberg, and I know she's very good in understanding your questions and replying very soon. So on behalf of Office of Research at Rockford, and I want to thank you, Anna, for your time, and all your sharing your experience is very valuable to all the postdocs and junior faculties to build their career. and it's a great impact on them. So thank you so much. And yeah, I think Vicky, you want to say anything?
No, I'm good. Just to let you all know, we are recording this and we'll make this available on the campus's YouTube channel. So if you know of others who could not make it today, please let them know that this will be available, again, both the recording and the slides.
Thank you, Anna. Thank you very much.
Thank you.
Thank you,
Thank you, everyone.
Thank you.